Swayam Prabha. Digital India. Educated India.
Welcome to the 35th lecture in mechanics of materials. The last lecture we started looking at stability induced failure. In particular, we analyze an ideal column. Okay. What I mean by ideal column is a column which is prismatic, straight, the load acting through the center of gravity of the cross section without any eccentricity in the load applied and things like that. Okay. We will provide more detailed explanations in this lecture on what an ideal column is. Okay. We said that we have to write the equilibrium equations in the deformed shape. Consequently, there arises more than one solution that is possible when you write the equilibrium equation in the deformed shape. Okay. We took an example of a simply supported column, we analyzed it and we found that two solutions are possible for certain critical loads. Okay. For certain loads which we call as critical loads. In particular, for a minimum critical load given by pi square E by lambda, lambda is L by R minimum square, that is the direction in which the minimum radius of gyration occurs, okay, squared. Okay. Then in that case your critical load is given by critical stress is given by pi square E by lambda square, which is called as the Euler critical stress, buckling stress. Okay. And then this was derived for a simply supported column basically. Okay. Now let us see how to get this Euler critical load for a different boundary conditions of the beam. Okay. First let us look at a cantilever beam. Say I have a cantilever column subject to an axial force P. Okay. Now what happens is the procedure is the same as a force acting P like that. Now this would have deformed into some shape like this, okay, and the load would continue to act perpendicular to the in the horizontal direction, okay. And if I were to say this displacement is absolute value of delta y, okay, and if I do a section analysis, if I cut a section here, if I cut a section there, okay, then I will have P here, P here, okay, and let us say this tip displacement is delta y max. Let us say the tip displacement was delta max y max. Okay. So now this distance would be delta y max minus absolute value of delta y, right, minus absolute value of delta y. Okay. This is also an absolute value of delta y max. Okay. Now then the moment is, this produces a clockwise moment. So I will have anticlockwise moment coming in here, okay. So I will have anticlockwise moment mz, which is P times delta y max absolute value minus delta y absolute value. Okay. Now I go back to my governing equation, bending equation, which tells me that E times Izz into d square delta y by dx square must be equal to mz, which is this is a negative moment here. So I will have minus P times absolute value of delta y max minus absolute value of delta y. Okay. Now I know it is a downward displacement, so delta y is negative. Okay. So this will be minus or minus minus plus P times delta y max minus delta y, because both delta y max and delta y are in the negative direction, both I have to put a negative sign, I pull that negative sign out, it will become positive. Okay. So, I have the equation E times I z z d square delta y by dx square is that. Okay. As before, this equation boils down to d square delta y by dx square plus k square times delta y is equal to k square times delta y max. Okay. Delta y max. Okay. So, basically for this the solution is delta y is again given by C1 cos kx plus C2 sin kx plus k square delta y max, no, plus delta y max. Okay. Plus delta y max. Okay. Now, I substitute the boundary conditions. The boundary conditions by the end A being fixed and end B being free are delta y at x equal to 0 must be equal to 0 and d delta y by dx at x equal to 0 must be equal to 0. Okay. This will tell us that C1 delta y at x equal to 0 is C1 plus delta y max, this has to be equal to 0. Okay. And then delta y at x equal to d delta y by dx at x equal to 0 will give us C2 k to be 0. Okay. Which means k is not 0 because k is a load which is applied, which is non-zero value, it depends upon the load that is applied. By the way, k here again means square root of p by e times I z z. Okay. So, k is not 0, so C2 has to be 0. From here you get the condition that C2 has to be 0 and C1 is minus delta y max. Okay. So, combining these things results, you have delta y to be given by delta y max into 1 minus cos kx, right. Okay. I substituted C2 is 0 and C1 is minus delta y max, but I have not used the fact that I have used the condition that delta y at x equal to L is equal to delta y max. Okay. That is a condition I have used because delta y max is delta y at x equal to L, right. So, if I apply that boundary condition, now I will get that delta y max into 1 minus cos kx must be equal to KL must be equal to delta y max. Okay. This would imply that two cases delta y max has to be 0 or cos KL has to be 0. Okay. This leads to a trivial solution where delta y, this gives us delta y to be 0 and this requires that KL must be 2n plus 1 pi by 2 pi by 2, okay, where n is 0, 1, 2 and so on. Okay. Now, from here you get the condition that P critical has to be, P critical minimum has to be pi square E I z z by L square 4 L square. Okay. Substituting n equal to 0, which is the first mode shape for this boundary problem. Okay. You find that the critical load for a cantilever beam is 1/4 the critical load of a simply supported beam. Okay. That is the observation. Okay. Now, let us proceed and do it for a statically indeterminate structure. Okay. Let us do it for a propped cantilever. Let us assume that I have a propped cantilever subject to an axial load P. Okay. Now, this would deform into some shape like this. Some shape like that. Okay. Wherein I will now what will happen is, even though there are no vertical forces applied, you will find that there is a reaction force developed, because this then supports a moment to be developed. Okay. So, basically that is why I am illustrating it with respect to a indeterminate structure. Okay. So, I have a P applied. Now, I cut the beam here as before. Okay. I cut the beam there and draw the free body diagram. I have that. I have a P. I have a P here, and I have to have a vertical reaction force VB. Let us say this is A and B. I should have vertical reaction force B there. There will be a vertical reaction force VB here. Okay. This is required to enforce the condition that the displacement at B is 0. Otherwise, there will not be a difference between a cantilever beam and a propped cantilever beam. Okay. This distance is x, and the length of the beam is L. Okay. Length of the beam is L. This will be L minus x. If delta y, as usual, this reflection is absolute value of delta y, that will be P times delta y, P times absolute value of delta y, because this distance is delta y, absolute value of delta y. Okay. Now, the mg moment would be in the clockwise direction, because both P into delta y produces a clockwise moment and anticlockwise moment, and Vb into L minus x, which is that distance, produces an anticlockwise moment. So, mg would be P into absolute value of delta y plus Vb into L minus x. Okay. So, this is the mg moment. Okay. Now, having got the mg moment, the procedure remains the same. I have to go ahead and solve the differential equation E times Izz d square delta y by dx square is equal to P times delta y is a negative displacement. So, I have minus delta y plus Vb into L minus x. Okay. This I can convert back using the standard procedure, defining k as square root of P by E Izz as d square delta y by dx square plus k square times delta y equal to Vb into L minus x. Okay. The solution for this differential equation is delta y is C1 cos kx plus C2 sin kx plus Vb into L minus x. Okay. Now, let us apply the boundary conditions. Now, delta y is C1 cos kx plus C2 sin kx plus Vb into L minus x. Now, delta y at x equal to 0 has to be 0, delta y at x equal to L has to be 0, and d delta y by dx at x equal to 0 has to be 0. Now, you have 3 conditions, that is, and we have 3 constants C1, C2 and Vb, which are to evaluate from these 3 conditions. Okay. Delta y at x equal to 0 tells us that C1 plus Vb into L must be equal to 0. get this from there. Delta y at x equal to L equal to 0 implies C1 cos k L plus C2 sin k L has to be equal to 0, okay. And this condition on the derivative tells us that C1 k times C2, okay, minus Vb has to be equal to 0, okay. Now from here I get C1 to be minus Vb times L, and from here I get C2 to be Vb by k, okay. Substituting that in here I get Vb into minus cos k L plus sin k L by k, allow L here, okay, by k equal to 0, okay. This implies that either Vb has to be equal to 0 identically, or minus L times cos k L plus sin k L by k has to be equal to 0, okay. This implies that delta y is identically 0 because of Vb is 0, C1 and C2 are 0, Vb is also 0. So, delta y is 0, which results in a trivial solution. This is otherwise, or from here I get it as tan k L must be equal to k L, okay. Otherwise delta y is given by Vb into cos kx into L minus plus sin kx by k plus x minus L. No, there will be a minus sign here, plus x minus L, okay. If P critical, if P is such that, if P is such that tan of k into L minus k L is equal to 0, okay. Solving this equation you can find the P critical value, okay. I am not going to go into that now, okay. I leave it as an exercise for you to do, okay, to find a P critical value, okay.